My dear students, welcome to my class. Today I am going to discuss with you one of the important periodic property, electron affinity. We have already learned about ionization energy. Ionization energy is which measure the capacity of an atom to change into cation. That means it's the amount of energy required to remove an electron from the valence shell of an atom. Just opposite to the same concept, let's discuss in detail. Here I have considered the fluorine atom whose atomic number is 9. So the electron configuration is 1s to 2s to 2p5. One more electron. Fluorine required one more electron to attain noble gas configuration or else the octet. So fluorine has the tendency to accept one more electron, right? So this fluorine is at is a neutral the fluorine atom at its ground level and which is gaseous, right, which is a gaseous state. So it has the tendency to accept one more electron. As a result of that, what will going to happen? If it accept one more electron here, fluorine get converted into fluorine anion, right, which is also in gaseous state, 1s2 2s2 p6. So which will attain the noble gas configuration. So when fluorine accept an electron, as a result of that, which occupy the position of the valence shell, it will liberate energy. Okay. So when an electron added into the atom, the fluorine atom at its ground level, it will liberate energy. As a result, a fluorine anion, a fluoride ion, F minus ion, and ground level at gaseous state is forming. This phenomenon is called electron affinity. In other words, it is a measure of the tendency of an atom to change into anion. The amount of energy released or liberated when an atom at its neutral ground level accepts an electron forming an anion at ground level. It is the amount of energy liberated or released when an atom at its neutral gaseous state at ground level accepts an electron to form an anion. So, as a result of that, this is an amount of energy released. So, thermodynamically, we can say that this is an exothermic process, right? Thermodynamically, we can say that energy is released from the system, which is an exothermic process. So, we can simply write the EA1, electron affinity. The first electron affinity of fluorine atom is negative in charge, which is exothermic. So we can illustrate it as if M is the atom which is at its neutral gaseous state at ground level, which accept an electron forming M minus, right, at gaseous level. As a result of that, EA1, energy get released. So the electron affinity, the first electron affinity is always exothermic, which is energy released. So what about the second electron affinity? If M minus accept an electron, right? If M minus accept an electron, is already been anionic stage, which is already been negative. So another negative charge, like charges when come closer, there is a repulsion between the two. Okay, right? When an electron which is also carrying negative charge, the atom, the anion, which is formed through first electron affinity reaction, which is also having a negative charge. So like charges, negative and negative, which come closer, gets repelled, right? So we have to supply or we have to apply some energy to overcome this electron-electron repulsion. So as a result, we have to supply some energy to form M2 minus at gaseous, right? So the amount of energy we have to supply to M minus to form N2 minus. This is called EA2, the second electron affinity. So we can say that the second electron affinity is always endothermic or positive the first electron affinity is always exothermic negative. This is one of the important concept of electron affinity. Okay, electron affinity is discovered by Linus Pauling in 1901. Linus Pauling in 1901. Okay, who's a chemist, scientist. 1901, he discovered electron affinity, and electron affinity is measured in the unit is electron volt or kilojoule per mole. Almost all atoms in periodic table has the capacity to acquire at least one more electron to its valence shell, and electron affinity is very important property to determine the periodic terms of almost all elements. But the actual fact is that the energy released when an electron added onto an atom, this value is very difficult to determine. In classical approach, the Born-Haber cycle of lattice energy is used to determine the electron affinity of most of the ionic compounds. But experimentally, it is very difficult. I will discuss in detail later. Now we discuss the periodic trends of electron affinity. This is the available data which is collected from one of the important theoretical inorganic chemistry textbook, Mr. Day and Selvin, and we can analyze why electron affinity is more important and how it changes across a period and down a group. So we can see that there are the electron affinity of certain group elements showing 0. Okay, so in the first group, first consider the first group, which is lithium, sodium, potassium, rubidium, and cesium. Down a group, we all know that moving down a group, the electron affinity value get decreases. Electron affinity get decreases. Do you know the reason? The reason is that because moving down a group, the atomic size increases, the atomic radii get increased. So as a result of that, the effective nuclear charge decreases. So the incoming electron does not feel much attraction from the nucleus. So the electron affinity also get decreased. So down a group, electron affinity decreases, which is a general trend in almost all groups. But in certain cases, we can see that some anomalies. So down a group, the electron affinity decreases. What about the second group? In the second group, the electron affinity almost 0. Do you know the reason? Because it is 2s1 and 2s2. So beryllium is 2s2. What about magnesium, which is 3s2 and 4s2 and so on? So we can see that the S subshell, the valence subshell is completely filled. So when an atom is having a completely filled electronic configuration, electron affinity is almost 0. This is the reason. So why the group 2 elements, this you can expect such a question, why group 2 elements showing 0 electron affinity? This is because the valence shell is completely filled. So due to the S subshell is completely filled, so there is the elements, the atoms doesn't have that much tendency to accept an electron. So the electron affinity of group 2 elements have 0. So we move on to the boron group. The trend is almost similar. So the electron affinity decreases, and there is an anomaly of boron and aluminium. And in the case of silicon and carbon, and the moving down a group, in the case of carbon family, we can see that the electron affinity is down a group, which is decreases. So in the case of nitrogen, see nitrogen across a period. So down a group, electron affinity decreases. Across a period, we can see that lithium is 59.8, beryllium is an unexceptional case, because of the completely filled electronic configuration. And boron, carbon which is getting increased, oxygen is increased, fluorine is increased, neon is zero. So across a period, electron affinity is getting increased because effective nuclear charge increases. So the electrons are more closer. The electrons are more closer to the nucleus. As a result of that, the incoming electron feel an attraction from the nucleus. So electron affinity also get increased. So across a period, electron affinity increased. Down a group, electron affinity decreased. But what is the speciality of nitrogen? So we all know that the electronic configuration of nitrogen, the valence shell electronic configuration is 2s2 and 2p, what? 2p3. So which is half-filled electronic configuration. Remember, in the case of group 2 elements, a fully filled electronic configuration is having nil electron affinity. Similarly, half-filled electronic configuration also showing zero electron affinity, approximately zero electron affinity. So that's the reason why nitrogen is showing zero affinity. Due to the due to half-filled p electronic configuration, the valence electronic configuration, nitrogen is showing zero electron affinity, and oxygen is 140 point, and here there is an anomaly is there. Down a group, there is a difference. See, oxygen is possessing in the oxygen group, in the oxygen family, down a group, the first we expect down a group electron affinity decreases, right? So here oxygen possesses the first element of the group possesses the lowest electron affinity than that of others. Similarly, in the case of fluorine and chlorine, you all know that among all the values, chlorine possesses the highest electron affinity. So you should remember this point. Among entire periodic elements, chlorine possesses the very high electron affinity, that is 348.5 kilojoule per mole, and that's the reason why chlorine is a very highest, very strong oxidizing agent. Okay, we'll discuss in detail. So you should remember there is fluorine and chlorine possess a difference in electron affinity because chlorine possesses very high electron affinity. Similarly, in the oxygen family, the first element in the group, the oxygen possesses the lowest electron affinity than that of others, right? Because sulfur, third period element, sulfur possesses the very highest. So these are the anomalies. We will discuss about these anomalies in the next class, next part. So see the noble gas, group 18, almost zero. Do you know the reason? Because of octet, S2p6 configuration. Noble gases having a completely filled electronic configuration. As a result of that, the electron affinity of noble gas is zero. And what about the D block? From scandium to chromium, electron affinity, the trend of electron affinity is gradually increases as we expect from going from left to right of a period. Scandium to chromium, chromium is 24, scandium is 21, 24, electron affinity increases. But there is a manganese which is zero because D5 electronic configuration, half-filled electronic configuration, and again getting increased, but zinc is a D10, 3D10, 4s2, right? Fully filled electronic configuration. So in conclusion, we can say that fully filled and half-filled electronic configuration, the elements having fully filled and half-filled electronic configuration, electron affinity is zero. In the zinc group, zinc, cadmium and mercury is having zero electron affinity. And please remember that lanthanides and actinides. So far, the electron affinity values of lanthanides and actinides are not found out. Okay, still researches are going on. This is the reason why finding out the value of electron affinity is very, very difficult, experimentally as well as in classical approach. So hafnium is having fully filled f orbital f14 and 4s2 and 4f14 5s2 5d10. So this is the reason why hafnium is showing zero affinity. But there is an exceptional case of gold. Gold is showing very high electron affinity of 222 kilojoule per mole. We will discuss it. So in general, we can say that there is anomaly that the group 2 elements is showing zero electron affinity and noble gases showing zero affinity. And whereas nitrogen, which is having half-filled electronic configuration, showing zero affinity, and in the transition metals, the d block elements is unusual. The trend is not, we cannot predict the exact trend of electron affinity in the case of transition metals, because the half-filled, fully filled configuration, the elements with the half-filled and fully filled configuration is showing zero affinity, whereas and the trend, the periodic trend of electron affinity is irregular. Okay, for lanthanides and actinides, electron affinity is so far not determined.